our next speakers are Devendar, Bureddy, and Manjunath, Gorentla, Venkata, and both are from NVIDIA. Just to give a short overview of their bios, Devendar Bureddy is a principal software engineer at Mellanox Technologies, currently at NVIDIA. He was instrumental in building several key technologies like SHARP, UCX, HCOL, etc. He was actually a developer, software developer of the MVAPICH project before he joined Mellanox. He has his master's degree in computer science and engineering from IT Kanpur. His research interests include high-speed interconnects, programming models, and HPC/DL software. And Manjunath is a principal software architect at NVIDIA. His focus is on architecting features for current and next generation NVIDIA's networking product, programming models, and network libraries. And previously, he was a research scientist and the language team lead at Oak Ridge National Lab. And there he did a lot of projects, including InfiniBand systems and Cray systems. He has served on the Open Standards Committee for parallel programming models, including OpenSMEM and MPI for many years, and is author of more than 50 research papers. He earned his PhD and MS degree in computer science from the University of New Mexico. So let's formally welcome Devendar and Manjunath, and they will be talking about UCC and SHARP, software and hardware building blocks for next generation collectives. So please, Devendar and Manjunath, share your slides and can get started.
Thank you, Dr. Panda.
Share the slides.
Yeah.
Can you guys see my slides?
Yeah, we can see.
Okay, and can you hear me okay?
Yes.
Okay, awesome. Thank you, Professor Panda. It's very nice to come and talk to you here. And what we'll do today is we'll talk about UCC and SHARP. The way we see UCC and SHARP is as important or key components, software and hardware components for accelerating collectives, particularly on the NVIDIA ecosystem. So I will talk about, I'm Manjunath Gorentla, and I'll talk about UCC. My colleague here, Devendar, will talk about SHARP. Let me go to, so this agenda. Given that this tutorial is fairly short, what I will do is I will talk about UCC as a project, like provide a more overview, and talk about our design goals and the solution space, how we thought about arriving at this particular solution, and then give a really brief overview of API, semantics, and roadmap. And then I'll hand over to Devendar here. So what's UCC? UCC is a unified collective communication API and library for collective operations. So if you have heard about UCX, it is a part of UCF, and complementing that UCX, which provides point-to-point operations on designed and implemented focusing on our hardware and other hardware. Similarly, we want to create something similar for collectives, and this is the effort. This effort started about a year and a half ago, so it's fairly new. And if you are already contributing to UCF, you don't need any other contributors agreement. You can contribute to UCC as well. A brief outline, I'll go over design, then properties of a solution, and then API, provide a brief overview of API, and really touch upon the reference implementation. I'll not go deeper in this talk, and then I'll touch upon what we are planning for next few months. So, so when we started this project, I think one of the important goals we had was to have a unified stack. What this means is we wanted to have a collective stack for HPC, DLML. This is a fairly obvious design goal to have, right? But the impact of that would be like, we need to support a wide variety of semantics. We need to optimize for different performance sensitivities, latency, bandwidth, and throughput, right? And then also we wanted to have a fine-grained control over the resource scheduling and the ordering model. For example, right, MPI and Openshift and UPC, for example, vary in their how the ordering can be controlled, right? And also this becomes obvious as I go through it. And also some of the workloads want ordering, some of the workloads doesn't want ordering, right? How do we provide this control? These are the challenges we had. Then for us, one of the obvious goal was to unify a stack, provide the same stack for both software and hardware transport. Software transport would be an example in our case would be something like we build a collective on top of a point-to-point library. Our hardware implementation would be provide a collective implementation on top of something like SHARP, right? Which this design goal, right? The challenges would be now we need to think about resource exhaustion, resource sharing, right? And when you have when you want to support an hardware, right, you might end up have to deal with like much more fine-grained semantics, like whether we want to provide a reliability or a completion in a certain way. So this added to the challenges. So another goal we had was unifying parallelism and concurrency. Concurrency here means that progressing the collective and also doing a computation at the same time, right? Parallelism here means you have multiple independent collectives progressing. So, and then another goal we had was to unify execution models for CPU, GPU, and TPU. So 2 years ago, it was fairly obvious that we wanted to run collectives on CPU and GPU, and whether it's a main memory or a device memory. And since then, also running collectives on DPU has become, has shown promise. And there's a lot of work done in MVAPICH group as well about the advantages. So what are the challenges with this, right? If you think about collectives, when you're implementing your collectives, so you have a thread that is invoking a collective and a thread that is executing the collective. Typically, when you have a CPU and a system with no accelerator, say, and you have just a main memory, typically this thread is the same. But when you go to say something like GPU and DPU, you might have calling the thread calling a collective, thread executing the collective might be very different. So we wanted to think about this in, I'm trying to characterize these challenges in as a way of execution model. So your two-way execution model means the control operations are tightly integrated. The calling thread and the thread that's executing the collective is the same. In such a case, what you could do is you can have multiple interactions with very low overhead. But if you go to one-way execution model where you have a calling thread and the execution thread kind of far away or decoupled, the overhead is higher. For such, you need to kind of make sure that you design collectives so that they are not interacting too much, right? Example of this would be a GPU or a DPU. So we knew the design goals. We kind of have an idea of challenges. We kind of know what the solution we were looking for, but what we were sure about is what the properties of this solution should look like. So, anybody in HPC community will agree that scalability and performance for key use case is very, very important, especially for the adoption of this library. So we wanted that to be an important property of our solution. Extensible. Here, extensible. We had so many requirements. We were sure that we possibly will not cover all of options and features that we needed for all use cases. So we have to keep our API and semantics pretty modular so that you can extend it. And then opt-in and opt-out. What I mean by that is, so there is many use cases we wanted to support. There are use cases that require certain functionality. There are certain use cases that doesn't require certain functionality. So we wanted to provide a mechanism so that you can opt in and opt out of a certain functionality. And so whenever we wanted to think about semantics, right, we wanted to make any semantic explicit rather than implicit. This is one of the design principles, and the solution we wanted to design should add this property, should need to have this property. So again, when you are supporting so many use cases, what happens is you will end up with a really large API surface area. We are very cognizant of that, and I hope we designed in a way that it's very easy to grasp. I will show the solution space. So if you want to think about a solution, you need to understand three components. There's only three components, and from there you can dig down and go into details. So first one is what I call abstraction. What I mean by that is, so in any communication library, right, there are resources, and the network, particularly in this case, would be a network resource, right? We wanted to build our abstractions around the resources. Here we have three abstractions: library, context, and endpoints. I'll go into detail, so I'll touch upon it. Teams, which is something similar to, say, if you're coming from MPI world, right, it would be MPI communicator. If you're coming from Openshift, it is Openshift team. So this is a global resource. So on these resources, we have operations to create, modify, destroy the resources, and other is to launch the collectives. So on these abstractions, right, we have a property, and we use properties this is a way for the user to express the semantics or optimizations required from the library. And you can think about this as a two-way negotiation. User is asking the library, okay, I need these features, semantics, and optimizations. And the library can decide to either support it, not support it, and you can query back these preferences. Right now, it's the features. The properties can be either on a single object, or it can be a cross-cutting feature. So we kind of see examples of both. So I'll pause here if you have any questions about a really high-level view. Then I'll dig into API a little bit. Okay, let me jump over. So I touched upon the abstractions. The abstractions that I will talk about here: collective, library, communication context, and teams. Let me jump there. What's a library object? The library object is encapsulation of all the resources required to for collective operations under group communication operations. So I'm kind of equivalently calling group communication operations and collective operations as same, but as we make progress in the project, we expect to see this group operations be beyond just communication operations. So what are some of the semantics on this library object is that all UCC operations should be invoked between the init and finalize. If you're designing any kind of a parallel system library, right, this is a fairly obvious semantic to think about. We provide a way to tailor the library to match the user requirements. Again, I'll go into details. The user of the library can be parallel programming models like MPI, MEM, and PyTorch. I give examples of this is because we already support all these. Or and I expect user could directly use this. I think it's simple enough that the users can directly use the library API directly. And the operations that we support are initializing and finalizing resources. So again, I'll touch back, right? If you want to think about our solution space, think about abstractions, operations, and properties. This is a grab of our header file showing creation of the library object. So this initializes a library. It takes in parameters. Parameters are a way to express the properties, basically saying what properties you require from the library. You can read directly in a runtime or through the environment. After initialization, you create a library object. So let's look at what are the properties that make sense for the library object. So this is again a grab of our header file. So in this, right, you have a thread mode. So the first one is mask. Mask basically says which are these fields are valid. The user might choose to only express thread mode, but not rest of it. Rest of it will be a default then. So the option for thread mode would be a single, a funnel, and multiple. Here, single means that in the application space, there is only one thread. If user tells to the library that there is only single thread, right, the advantage would be the library implementation can be implemented kind of lock-free, because you know that there's not multiple threads trying to access it. Next property is collective types. Sorry.
No, I think that was like background noise. Please proceed.
Okay, no problem. So collective types, basically the user can tell what collectives the user is expected to use out of the library. We support all standard collective types that is required for MPI, SHMEM, and PyTorch. I mean, reduction types is also similar. If we tell the user can tell the library what reduction types that user expects to use. Synchronization type, I'm not going to detail about this, but I'll be very happy to talk about it. But the main idea is, right, the collectives can be synchronous or asynchronous. And in fact, UPC defines 4 different models. The idea is like a synchronous collective would be like, we'll start a collective when all the participants of the collectives are ready, and we'll complete the collective when all the participants of the collective are completed. This is a pretty strong semantic, and you might actually not require that semantic, but it's also a useful semantic. So we kind of want to support all these synchronization types, and also we want to give this control to the user to ask for a certain synchronization model. And the reduction wrapper here is a way to provide a user-defined collective that's probably mostly used in MPR. So those are the properties that we can customize for the library. Sorry, your question?
Yes. So what are sync types are currently supported? Like, is it just synchronous, like for instance, barrier? Or do we have other types as well?
So this is, I would say, is a bit different. Say that I will take an example of, say, let's take all-to-all, right? What I mean by is the property can be asynchronous or synchronous. What I mean by that is, right, say a participant enters all-to-all collective. In the case of MPI or SHMEM, right, I don't need other participant to start the collective. You can start progressing your collective on the local, say rank 0, for example, can start the collective, right? It can send the data and receive the data. On the synchronous, if you think about synchronous collective, we want everybody to be ready before starting the collective. Let's take an example of OpenShMEM, for example, right? In OpenShMEM, I can really progress the collective without other participants starting, because when I start any local process starting, I know the remote address, I know the remote buffer, right? I can start putting my data there. So if the user is confident that their workload doesn't require the synchronization, you can just start, and it gives you a certain performance advantage, right? But if your workload is not confident that the buffers would be ready, they want to do the synchronous collective, right? So we wanted to decouple this implementation into multiple components and give the user to build it as required.
I had a question as well.
Sure.
So is the main goal of this to like, does this impact SKUs, or like, what was the main goal of having this?
So the main goal is basically, right, what we see is certain workloads and certain models doesn't require this. So one, we needed this from a programming model perspective. If you think about UPC and SHMEM, right, they define this, especially UPC, right? They define 4 different synchronization models, one. And so some of the workloads actually can leverage this. Particularly something like in PGAS world, right? What you could do is many a times you just want to start the collective, and you know the address, remote PE or rank, and also the buffer address, right? So you can start doing the collective. So and what also happens is many of the PGAS workloads, they just do barriers much earlier, and they don't need another synchronization during collective implementation itself, right?
Right. So all this would also be affected by the algorithms that are used, right? For example,
Yeah.
So okay, I guess that you will be explaining in subsequent things. Or does UCC even focus on algorithms, or is it just like an API to?
No, we have a whole implementation. I mean, if you go to the GitHub, right, we have an implementation. We are, I would say, it's fairly early, but our goal is to support API and the library implementation, both software and hardware. And we have a code running at some of our customers as well.
Okay, thanks.
Yeah, but I'll not be touching upon that in this talk because it's, I don't think I can cover it. So.
Yeah.
Okay. So jumping ahead, right? I'll skip this because I already talked about this. And next, I'll talk about another abstraction communication context. Okay, what we do now is we just created a library object, and you can use the same library object for multiple programming models in application, or you can choose to create multiple library object, right? So now, if you communication context is object to encapsulate local resource and to express network parallelism. What I mean by that is, right, so one of the important network resource for a communication operation would be like a HCA or a network card, right? Like on that, typically most modern network interfaces, right, HCAs will have parallelism. And this is a way for us to capture those parallelism. Say that a certain network card has 8 pipes, right? Where I can push the data on 8 pipes and progress it. You want to probably have 8 communication context, right? If you think about that, we are thinking about this from a ground up kind of a way, right? So the network resources can be something that's parallelism on the network card, or it could be just an injection queue. So this API provides, gives you a flexibility to design certain way, right? So you can couple this communication context to a thread, which is what typically you end up doing, or it could be threads or a task, right? You can couple it. This can be used to provide affinity. Basically, you can say, okay, for this core, I want to have this context, and based on that, I will build the rest of the team and so forth, right? And this could be a way to do resource sharing. And also another way to think about this is, say I have a software collective, software transport and a hardware transport. I should have multiple contexts reflecting software and hardware, so that I can take multiple contexts and build a team. So I'm not introduced the team, but I'll introduce. The team is nothing but a communicator. So we have a library object, then we have a context. Context is nothing but a local resource. we group this network resource, local resources into a group to create something like a tree. So let's see. So this is again an interface to create the context. We are passing in library handle. We are passing in parameters. And the parameters are again properties of the context, where user can express what are the semantics they want from the library. One way to read is through the runtime or environment. And then the output is to create a context. I will not go into all the properties, but one of the important properties is you can create a context either as exclusive, which means that the context is participating in a single team, or it can be shared, which means that it is participating in multiple teams. So this becomes a choice for the user to create a resource and use it exclusively in a single team. Probably this is more useful when you want to get a higher performance, say higher bandwidth, right? Another way is you can create multiple contexts reflecting the network parallelism or number of HCAs, and then you can use set of contexts to the same team, which means that you can maximize your bandwidth. And say that you don't need to maximize the bandwidth, right? Then once you run out of your network parallelism, you probably want to end up sharing your context. So you can create a context in a shared mode and share it with multiple teams. Next is teams. So we created a library object, we created a local resource, then we'll create a group resource. So group resource is nothing but a team. So this is your abstraction for collective operation. The collective operation runs on this abstraction. So I'll go a little bit faster because I took 27 minutes already. We create we create, let me skip to next. So to create a team, right, we use this interface. It takes in context, array of context. As you remember, it's nothing but all the local resources that we created. Every participant should provide a context. This is number of context. Again, team parameters. Basically, it takes in the it's a way to customize the team, and as output you have a new team created. Again, right, you are seeing the pattern. It's every time you do, there is a negotiation between the user and the library how to create this abstraction. The import, I'll touch upon briefly all these properties. So mask again will say that, okay, what are the fields that's valid here. Ordering here says that whether you want to have a collective to be ordered or not, meaning that every participant should participate in the same order or not, right? If you have multiple collectives, it makes sense. Then we have outstanding collectives. Basically, this is an int, so that if user says that the user will ever use only one collective, right? We don't have to create a lot of buffer space. Endpoint. Endpoint is nothing but, think about it's a rank in a communicator. It's basically the participant ID in the team. Don't worry about EP list and EP range for now. Team size is basically number of participants. So the reason we provided the EP, right, so that if MPI is using UCC, it can pass in the rank directly. If you want to use it directly without MPI or anything, right, you probably want to create this as a output parameter. Then again, you will see sync type. Again, it can be synchronous or asynchronous. And OOB here is so when you want to create a team, right, you need a collective to build the team, at least the first collective. After that, you could use the split operations. So if you have already some other way to boot up the library, right, you can use that. Or if we plan to also support when there is no support for that, meaning that you can pass in null and internally we'll implement our OOB. So P2P connection is a way to do resource sharing between a point-to-point library and a collective library. Memparams is a way to attach a memory to the team. This is particularly useful for something like a PGAS. And EPMAP is basically, we need to have a kind of a basic, what we want to do is map between context and the team itself, basically resources to participant mapping. And ID is team ID. If you're coming from MPI world, you can think about this as a communicator ID. If you already created somewhere else and you need that ordering between the teams, right, you want to probably provide this. So, so these are basic resource abstractions, collective operations. I'll just go this again. Again, collective operations, right? We didn't decide to do blocking, non-blocking. Rather, what we did was we said, okay, if we decompose all the requirements from blocking, non-blocking, and persistent collectives, what are the building blocks that's required? And we have a building blocks, and you can combine this in a various forms to realize either a blocking, non-blocking, or a persistent collective. For example, here init collective init will just initialize the collective. It will not execute the collective. Basically, it prepares the connections, buffers, and so forth. Collective post will post the collective, and init and post is basically combine this into one, and collective finalize will finalize the collective. So, I mean, if you think about persistent collective, right, it maps similarly, it maps to that variable, right? Init where you initialize the collective, post, you can do multiple times post the collective, and finalize, after finalize, you cannot post it unless you initialize it again. So I probably can skip this because this is, I already spoken about it. Here, what I'm showing is how to build blocking collectives, for example, init and post. And once you do test and finalize in the same function, right, you're getting a blocking collective. Persistent collective, you can map into init, post, test, and finalize. Also, if you want to implement a split phase collective, right, you can do init and post. You can set the number of outstanding collectives to 1 and do test and finalize. So currently we do mostly blocking and non-blocking. We have a very rudimentary implementation of persistent collectives, not very optimized yet. So with this, right, you have a basic abstractions required for implementing MPI collectives, non-blocking collectives, both for MPI and SHMEM. So then we wanted to go support say GPU collectives, GPU collectives, DPU collectives, right? A collective that runs on a DPU or that leverages GPU for reduction, for example. So what we did was we wanted to think about this in a little bit more agnostic of GPU or DPU way. As I mentioned in earlier my presentation, right? You can think about this as a two-way model, two-way execution model, or one-way execution model. The abstractions to realize is this. So let me talk about execution engine. What I mean by execution engine is nothing but an execution context that supports event-driven execution on CUDA stream, CPU threads, and GPU threads. Let me expand on that, right? So if you think about like a vanilla setup where you have a CPU running collectives on a CPU, and the data is in the main memory, right? Here, in that case, the execution is nothing but just a CPU thread. So we always have this implicit implementation, we have been implicit about where the execution happens and so forth. So there was probably no need to abstract that out. But as we move into these architectures of GPU, DPU, and more, right, we need to abstract where the collective runs. And this is our way to abstract that. So that we are calling an execution context or execution engine, where the collective runs. And in the last few slides, right, I also made an assumption about how the collective runs. I post a collective, it just runs right away, right? And the control thread is controlling when the collectives get executed. In an execution engine, right, what we do is we try to abstract that out, and the executions happen not because of a certain control thread reaching a certain point, rather it happens on an event. So based on an event, a collective can be executed. So that's our idea here. The execution engine, so execution engine can be CUDA stream, CPU thread, or a DPU thread here. And when does any operation happen on this execution engine? When you have an event, either a library generated event or user generated event. So if you go back to the previous slide here, the post, right? For example, when user calls a collective post, the collective gets executed right away. We introduced triggered operations. In the triggered operations, what happens is, right, you post a collective, but it doesn't execute until certain event happens. So we can customize a team whether to have an execution engine with events or not. So this is something, again, going back to our philosophy of customization for each of these abstractions. So I'll take an example to see how this could be useful. So here, right? What we want to do is we want to have, we have one application communication thread that is preparing the collective, and another application thread that is starting the execution of the thread. So you can imagine the mapping from here to, say, GPU collectives or DPU collectives. So first step one, right, application prepares the collective operation. In this case, the UCC library's collective init and triggered post will get invoked. The collective is not executed yet. So on a second step, when a certain event happens, say, for example, you completed a compute in a certain thread, right? Then you could basically that when the event is triggered, your collective gets executed. And then once the collective gets executed, another event is generated called the collective complete. Collective complete will generate, on the collective complete, there is the event generated, and that based on that event, the application thread can pull the execution engine, and you will you can go you can get the information from the library saying that a certain collective has in. So I'm sorry, I had to rush through this. Do you have any questions so far? Okay. So I went really briefly into the API, but if you want more details, right, we have a specification. You can download it from GitHub. You can pull and build it yourself. I have a PDF that is built. So now going to the implementation, again, I said I'll not go into details, but I'll touch upon it. This is the component architecture, components in the implementation that we have today. Applications can directly use UCC, or we have support in OpenMPI currently, and we have support for OpenShift and PyTorch. We don't have support for Legion Parsec, but you could use it if you want it. Below that UCC, there is an internal API. This reflects very close to the public API. Only addition is how to manage the components here. And the core component will have an implementation of most of these interfaces. And then you can think about there is two layers called a CL layer and a TL layer. TL layer is a team library layer or team layer. What it is you can think about it's a basic collective primitives. We have an implementation over UCP, basically UCX, and there is abstraction over nickel. There is no abstraction of SHARP yet, but that's part of our roadmap. And this will become, so if then you have a collective layer which composes these multiple team layers in together. Currently we support only basic, but we are already working on something more optimal hierarchical implementation. Then the yellow boxes here are basically the utilities required. So let me go into next step. So we are making a lot of progress. We plan to release probably this week or next week, first beta release, and then we'll have a more stable release. Maybe we are targeting SC. So currently we support CPU and GPU collectives. We support actually MPI. We support PyTorch. And for later this year, we plan to support hierarchical collectives and also SHARP likely, and hopefully persistent collectives as well. And we hope to have more performant implementation by end of this year. And then we plan to have series of 1.x releases, basically targeting DPUs, DPAs, and also have more stable releases. Probably 1.x series will be more next year once we achieve 1.02 this year. So again, this is an open source project. Ideas, code, documentation, everything is welcome. There is multiple ways to participate. If you're interested, please participate. So I'll pause here. I'll take a very quick questions and then hand over to my colleague Devendar. Any questions? Okay, Devendar.
Can you hear me?
Yeah, Devendar.
Yeah. Okay. For some reason I'm okay. Yeah, thanks Manju for covering in brief about the UCC. So SHARP, so I would like to touch base on the progress we made from the past year. So we had a SHARP tutorial at MUG from the very beginning, and every time we are covering in detail about how to use it, what are the components. So this time we thought about introduce UCC, and so I will cover the progress we made from the past 1 year. So brief introduction. So the in-network computing. So this is a motto for the Mellanox networking hardware. So we want to offload the part of the compute from traditional cores to the network. So that we can use the CPU or GPU for main computation instead of just processing the data. So we are thinking, so we are in the core design, we are rethinking the boundaries between the components. So traditionally we were moving the data into the core and processing, and then we are again exchanging. So we are using networking only for the transferring the data, but here we want to do, while data is moving in the network, we want to do compute as well. So the SHARP is a scalable hierarchical aggregation and reduction protocol. So here we are offloading the reduce operations onto the fabric while data is moving. So if you take traditional all reduce algorithms, where you have a tree-based algorithms or ring-based algorithms, where you get the data into the host and you compute it, again send it out to the other host. So most of the algorithms is optimal algorithms is logarithmic scale, and the amount of data you exchange to realize the all reduce operation is typically 2x. So data needs to be sent and received twice to realize the all reduce operations. So here in the SHARP protocol, basically every host is like offloading the data to the fabric, and the fabric is computing, and you just receive the final result of the all reduce operation. It's like a send, the all reduce became just like a send and receive operations. So the SHARP, it's a tree-based aggregation in the fabric, and it support multiple operations, and simultaneously it's a optimal protocol for MPI and deep learning applications as well. It supports barrier, all reduce, reduce, and broadcast, and it supports many type of operations. For example, if you take the MPI reduction operations, it supports all set of operations and except multiplication, and many data types as well, integer, float, and even float 16 as well. So yep, so while data is moving in, we are aggregating and just we are getting the aggregation results back to the host. So SHARP is its generations. So SHARP 2.0 is a current quantum generation SHARP protocol. So SHARP 1.0 was only targeted for the small vector reductions, but 2.0 is supports small vectors. It's improved small vector reductions, as well as we introduced something called streaming aggregation. So this is a high bandwidth reduction operations which can be performed at the line rate. So it is mainly focused for the deep learning applications where the size of the messages are megabytes and gigabytes. So so the SHARP 2.0 is introduced this streaming aggregation protocol. And also SHARP, it works with in conjunction with the GPU direct RDMA protocol, so makes it is more suitable for DL. So now you can stream the a large all reduce operation from the GPU to the fabric directly, so without staging it to the host. So the streaming aggregation is a killer app for distributed and synchronous deep learning frameworks, where you need to synchronize the gradients at in each step of the training. So it's not only so in the recent MLPerf v 1.0, so NVIDIA achieved record-setting performance with the SHARP. So I put the link here. So the SHARP is a critical piece in achieving this performance on Selene supercomputer. So what are the new features added from the past year? So now SHARP is cloud ready. So now we successfully installed it in the Microsoft Azure cloud infrastructure. So we needed to added new features for enable this. So one thing is the SHARP the SHARP daemons. If you there are components sitting in the aggregation manager node, where basically the OpenSM server, and which needs to talks to the compute node daemons to exchange the control path messages, like creating the SHARP request in the fabric. So those communications were earlier, it was TCP/IP, but in clouds, those are, there is no connections between, there is no explicit TCP/IP connection between these components because of the security reasons. So now all the daemons talks with UCX based in-band communication using DC protocol. So it's optimal, low latency, as well as it provides the security for the clouds. And also we added the PKey support. In cloud, every user gets a partitioned fabric. So we need so for the security reasons as well. So we need to add the P key support in building the sharp trees and provide for the and for the communication as well. And GRH, the global routing. So the cluster at the Microsoft Azure, the OpenAI, it is so big that we ran out of the 16-bit LID space. So now we need to enable the GRH based routing. So it also we also added this support and exclusive lock. So so SHARP is a limited resource in the fabric. So there is a possibility that there is a contention between the users. So the exclusive lock feature is basically to guarantee the resources for a user. So when they deploy their application, they can select, say that I need exclusive lock for these resources. So so that he will get a dedicated resources and better event reporting integration with our fabric management tools, UFM, to report what type of events happened in the SHARP, like if there is any errors or if there are any link loss, or all those events are reported for monitoring. And also we improved the connection keep alive between the daemons to reuse the connections. And also topology API. SHARP knows the whole fabric topology because it needs to build the trees, right? So we extended the SHARP API to give this topology to the user in case if you want to use this for any of the other further optimizations. This is a low latency SHARP performance. So I mean, you can see that with SHARP, you kind of getting a constant latency. The jump for example, in the all reduced latency plot here in the left side. So the host based algorithms are the curve is going up because that's logarithmic algorithm, and whereas SHARP is kind of a constant latency. There is a jump from 8 to 16 at 16 nodes because you are moving from one switch to the to one level to the 2-level tree. So the latency will be added will be only the switch latency, and it is expected to be the constant once you are in that level. And the right side, it's at the customer reported and shared data is basically, we can see that the latency with the SHARP is low compared to the host because because it's offloaded to the fabric. So this is on the Selene. Basically, I would like to highlight is basically we ran in, this is up to 128 A100 servers and 1000 GPUs. And this is Nikhil all reduced performance with and without SHARP. So if you see the without SHARP, basically 8 nodes, this is the red line, and once you are upping the scale, the curve is shifting towards the right because it's a logarithmic, and the latency is going to be affected with the scale. Whereas if you see the SHARP curve, so the latency of 8 nodes is same as the latency of 128 nodes here. And so there is not much difference. It's and the typical deep learning message sizes around 128 and 256 megabytes. The difference is even more than 2x and 2x. This is a critical, I mean, optimizations which enabled to achieve MLPerf record setting MLPerf results on Selene. And this is shared by the Microsoft. So this is on Azure cloud. Recently, we performed, we compared SHARP and non-SHARP there. this is at much scalar scale. So the right side is the left side is without SHARP. The peak is is limited by around 128 gigabytes, but with SHARP it received 200 and around 210. And the main thing is it's same for any, it's more or less same for any scale. So that is the, I mean, a key point is here, that it's very scalable solution.
So Deva, just a quick question. So does Nickel, the released version of Nickel have support to use SHARP right now, or is this some internal version?
No, it is by default. It is
It is
public
by
for
default.
public. Yeah.
Okay. Thanks.
Yeah.
And
so
one other thing. So will SHARP work if we pass GPU buffers directly to it right now?
Yes. Yes.
Okay.
Yeah.
Okay. Thank you.
Yeah. This is a performance. Yeah. And yeah, that's it. These are the main thing we enabled, made it the cloud ready, and the solution is tested at the scale, and we achieved greater MLPerf results. And in the next generation, I didn't make it here, but the NDR generation have a even more scalable features. And currently, one limiter factor in quantum switch is that the fabric needs to be rail optimized. That means all rail needs to be rail 0 from one server needs to go to the same leaf level switch, because currently we can do only 2 streaming aggregations per switch. So these limitations are removed in the next generation NDR. So we are expecting it to be seen in the Q1 next year, the SHARP with 3.0. Yeah, with that, yeah, we are open to the questions, both on UCC and SHARP.
So thanks Devendar and Manjunath. So we have a few minutes for the questions. Those who have joined a little bit late, you can ask questions under the Q&A buttons. We also have a Slack channel. So either way will be. Or if you would like to directly talk, we can unmute you, and then you can.
Yeah, you can just raise your hands if you would like to talk. In the meantime, while I have Deva and Manju here, let me bug them with a few more questions.
Right.
So, is there a particular version of SHARP that is required and a particular version of switch that is required to support GPU buffers?
No.
Okay.
It's supporting GPU. All you need is NVP mem. That's it. It's nothing to do with the switch, because only at the host. The solution is only at the host side.
So basically, the SHARP daemons are the ones which will be doing the GDR and then sending the data out. Is that right?
No. The MPI process, which is the MPI or user process, which you are passing the GPU buffer to it. It's basically SHARP is nothing. You have a QP from host to the switch, right?
Right.
So that QP is RC based, so that can read the GPU memory and send it out. So it doesn't know anything about SHARP, or the GPU direct doesn't know anything about SHARP or not. It just taking the data from GPU and sending it over peer-to-peer to the fabric.
Okay. Is there any recommendation, like a tuning recommendation, saying that until this message size, we can directly pass the GPU buffer, below this or above this, please stage the data to the host and then pass it? So is there some recommendation like that you guys have?
So right now, it's for small message protocols. So host side, it uses the GPU direct RDMA, but the receiver side, it will be staged to the host. Then either it uses the GDR or CUDA copy for that.
Okay.
But SAT, it can directly move data from user buffer to the user buffer.
Okay. So we have a question on Slack. This is from Benson Mute. Do you expect others to directly build communication libraries on top of UCC and UCX? Pi UCX is interesting, but MPI for Pi is much older and seems unlikely to be displaced.
I can take the UCX in general, right? I think it's not a bad idea to build on UCX or UCC, right? Especially if you're not tied to a particular programming model, say MPI or SHMEM or Torch, right? I think both UCX and UCC is not that complex to comprehend, and the APIs are well defined. We try to maintain very stable interface, at least UCX and UCC. That's our plan to have a. So yeah, and we have a UCX for Pi, right? Support as well. So if you're not tied to a programming model, why use it?
Sure. Thank you. I think that's about all the questions I had.